avons le plaisir d'accueillir Philippe Boalch, du CNRS, l'Institut de Jussieu, qui va nous parler de First Step Global Leaf Theory, Why Riemann Surfaces, the Character Varieties and Symplectic Structures.
Merci. C'est un grand plaisir d'être là. Je vais peut-être parler en anglais parce que j'ai écrit mes transparents en anglais, mais j'espère que ça va. So this is supposed to be a kind of a survey talk. There's a course which I taught, and about half of the lecture notes are on my webpage here. So that will probably be a bit more systematic than this expose, but hopefully something will be transmitted. So let me start with two questions. So I got to this subject. I was interested in understanding geometrically what the Painlevé equations are. So the Painlevé equations are these sort of objects. They're things like, the Painlevé 1 equation is like y double prime is 6y squared plus t. There's this family of equations that Painlevé discovered, basically because they have good properties. And in particular, he discovered them because they're deformations of equations for elliptic functions. And so here, it's possible to put a parameter such that if you scale it, you get to y double prime is 6y squared, and then it's possible to solve this in terms of the Weierstrass P. So you can easily get from here to y prime squared is 4y cubed that can be solved as a particular case of the equation for the Weierstrass P. So he has these 6 families of equations which are equations for functions which are deformations of the theory of elliptic functions. So geometrically, they're extremely interesting objects. And you would like to understand, sort of how to think about them intrinsically. Most of this was actually worked out by Okamoto in the 1980s, but the question then becomes how to understand in such a way that it generalizes to the analogues of the Painlevé equations of higher order. So I looked at this in my first paper in Advancing Math in 2001, and basically the geometric way to understand them was to read the papers of Simpson, who had this very general perspective on non-abelian Hodge theory. And in particular, he talks about the non-abelian Gauss-Manning connection for an arbitrary family of smooth projective varieties. So any such family gives you a non-linear differential equation, a connection, an Ehresmann connection on a fiber bundle over the base of the deformation. And comparing that with the Painlevé picture, it was clear that the Painlevé 6 equation is the simplest example of a non-abelian Gauss-Manning connection. If you take the family of 4 punctured spheres and take the group to be SL2, then Painlevé 6 is an explicit expression of that intrinsic connection. So thus, if you read the rest of the papers of Simpson and Hitchin, that gives you a nice geometric language in which to try to understand the rest of the Painlevé equations as well. And that's really what leads to this picture of deformations of wild Riemann surfaces, how to understand in the same way what a Painlevé 1 to 5, given that we understand Painlevé 6 as a completely geometric, non-linear equation. So Poincaré said that the work of Painlevé is an island which is in a neighbouring ocean to the rest of mathematics, which is connected. And now perhaps we understand better, what he actually did. He discovered the first examples of non-abelian or non-linear gauge theory equations. So these are equations like this, which are best understood as being equations where the unknown is a connection on a vector bundle. So in these particular cases, it's a meromorphic connection on a rank 2 vector bundle on the Riemann sphere. And so it's really the start of something which is nowadays quite well known, but it's perhaps not appreciated that it goes back to this work on the Painlevé equations. So a more general question is to understand geometrically what is the Riemann-Hilbert-Birkhoff correspondence trying to tell us. So this is the generalization of the map that takes the monodromy, the representation of the fundamental group, to the case of connections on algebraic curves, connections which have higher order poles, which have irregular poles. So it basically says that there's a vast amount of stuff there which generalizes the representations of the fundamental group, which everybody knows and loves. So those are the two questions at the start. So now I want to explain part of the answer and then go back and repeat the question in a more explicit way. So the talk is quite complex, so I thought it would be good to try to make a clear statement close to the start. And so there's this picture. If I fix a complex reductive group, if I have a compact Riemann surface, I can attach to that the character variety, the space of representations of the fundamental group, the Betti moduli space, taking the affine GIT quotient of the representation variety by the conjugation action of the reductive group G. So this is a way to attach a space to a surface, and if I deform the surface such that it's, say, smooth, I get a local system of character varieties over the base. And that is the geometric reason where, why all of these non-linear differential equations appear. That they're just the de Rham version of this Betti picture here. And this has a large extension. So for instance, this picture at the top, if I look at a four-punctured sphere, would be the way to understand panel of A6 for G being SL2. And then to understand panel of A1 to 5 and all of their generalizations, you want to upgrade your notion of a Riemann surface to have part of the boundary data as well, the irregular class, or the extra modular parameters, which obey just like, which have the same properties as the moduli of the surface with marked points. So you will attach to this a certain space of generalized monodromy data, and if you read the papers very carefully and change it a bit, it's possible to view this as a quotient by a reductive group H of an affine variety, the space of Stokes representations. There's a wild surface groupoid here, which generalizes the surface group at the top here. And this is affine, and we can look at the affine GIT quotient of this by the reductive group H. It's slightly different than the picture at the top, that we have to change the group. Basically, there's a grading which is happening at the boundary, and H here is the graded orthomorphisms. But nonetheless, the basic picture is the same, and to each such surface, we get this wild character variety MB. So one of the main algebraic statements is this, that basically the analogues of statements at the top, that first of all, the wild Betti space is an algebraic Poisson variety. It has a natural Poisson structure. And the points of it are the reductive Stokes representations. So the version at the top, there's a theorem of Richardson, which says that the closed orbits are exactly the ones whose differential Galois group is a linearly reductive group. These are the reductive representations. The differential Galois group in the tame picture at the top here, it's just the Zariski closure of the monodromy, the image of the representation in G. And we proved in January that the same statement works in the irregular case as well. So Ramis has a theorem which gives a topological description of the differential Galois group in terms of the Stokes representation and the exponential tori. You look at the Zariski closure of that, and that is exactly the condition. If that group is linearly reductive, that's exactly the condition for the orbit of H in R to be closed as well. So the points of this are the reductive Stokes representations extending the statement at the top. And then finally, we also have the statement, if you vary the wild Riemann surface, so the surface and the marked points plus this part of the boundary data as well, the irregular class, again, the spaces MB form a local system of Poisson varieties. And that explains, that's the basic reason how we get these sort of generalized or irregular non-abelian Gauss-Manning connections that you need to sort of enrich the geometric picture by adding on part of the boundary conditions as well. So that's one way to think about what the panel of A equations are trying to tell us, that there is this picture. So most of this was approved as a sequence of results, and the last step is in this paper with Yamakawa in 2015, and the statement about the reductive representations was in a paper this year. So let me back up a bit. I have this sort of fancy title. So I want to justify that slightly. So there's this standard picture that I can look at the exponential map. For instance, if I take G to be GLNC, I can look at the Lie algebra, and I can look at the Lie group. So I have an additive side and a multiplicative picture. And you can look at the map, the transcendental map, which takes an element of the Lie algebra to an element of the Lie group. And it's a trivial remark that one can see that as taking the monodromy of a very simple meromorphic connection. You just put x over 2 pi I dz over z, so I have a complex disk, and I have this meromorphic matrix of one forms, and taking the exponential map is the same as taking the monodromy around a disk, around a loop around the puncture at 0 of this very simple connection. So if I phrase it in this way, there's an obvious generalization. Suppose I take an arbitrary matrix of rational one forms, then can we attach data to that such that there's a generalization of the holomorphic maps at the top? So this was first looked at by Birkhoff in 1913, and he said that for generic rational one forms, if you take the leading coefficient at each pole to be regular semi-simple, then there is a space of data to put here which has the same dimension, that there is a magical object there which generalizes the representation of the fundamental group, which occurs basically in the tame picture, this simple pole case. So that gives you the group-like object which corresponds to an arbitrary, a generic rational matrix of one forms. So this is the type of data that we want to understand geometrically. So there's a slightly more intrinsic perspective. So here we're looking at meromorphic connections on the trivial vector bundle. We can look at moduli spaces of these by having a look at them up to isomorphism and the ones which are stable. And so we could get a holomorphic map between two spaces of the same dimension. So the basic question is, what are the conditions we need to fix at the poles such that you do get two spaces of the same dimension? We know from Birkhoff that it does work for the generic picture. And basically, I think we now understand a much larger class of cases. So there's a long story about putting a Poisson structure on these spaces, and we'd like to know which are the symplectic leaves that we're allowed to pick such that there's a corresponding monodromy space of the same dimension. So in a moment, I'll get to the definition of good connections, and we think that's the right moduli problem to have a look at. This can be souped up, that the map here, which is like the analog of the exponential map, which is neither injective nor surjective, this map can be improved by factoring it. There's a Dirac moduli space such that we actually have an analytic isomorphism. So there's an algebraic inclusion and then an analytic isomorphism between a precise Dirac moduli space of meromorphic connections and the Betti space over here. And then there's this way to introduce a Hermitian metric as well, that There are stability conditions on these. That's the condition for the existence of a Wiles harmonic metric. So these are the Hitchin equations on the open curve. And you can also get the correspondence with meromorphic Higgs bundles as well. So at the end of the day, you get this picture of having like a Lie algebra type space over on the left, and then all of these spaces are isomorphic. There's an analytic space, some hypercalar reduction, and then it has these three distinct algebraic structures. And so we would like to view these as some global analog of a B group and try to classify and look at the representation theory of these spaces, pretending that there's something like a B group. So in versions of this talk I gave before, I would now jump over and suppose that part is known and start talking about how to classify these spaces in terms of Dynkin graphs. For instance, there's a large number of cases that just have one irregular pole where M star is isomorphic to a Nakajima quiver space. And so we get lots of generalized multiplicative quiver varieties as the full non-abelian Hodge space here. But I think to this audience, I should back up a bit and explain a bit more about what's happening in the circle and the history of it a bit more, because there's lots of confusion in the literature. So people should feel free to stop and ask questions if it's not quite clear. So there's this big picture. So there's basically three groups of people that work in these three different algebraic structures. There's a long history in the integrable systems papers. So I basically started over in this picture here. So the Panlevet equations and the isomonodromy equations are the equations for monodromy and Stokes preserving deformations of rational differential operators. If I take the dz there and multiply through, I have a connection on a trivial vector bundle, and so it embeds into this picture in the middle of the meromorphic connections here. There's a story of taking the autonomous limit of this to get these isospectral deformations, these rational Lax matrices. And these will be solvable in terms of the spectral curve. And you can also go in this way and take the monodromy and Stokes data, and these are basically the integrals of the Panlevet equations or the isomonodromy equations. So you have these three pictures, and then Hitchin came along and said, well, you can actually replace the base curve by a curve of arbitrary genus, and you get this notion of a Higgs bundle at the bottom here, and there's a correspondence between the stable Higgs bundles, the holomorphic connections, and the representations of the fundamental group. Here I'm thinking of the picture of having a compact surface. So you should be able to put these two pictures away. The picture at the bottom gives a much more sort of clean and sophisticated language that you would like to extend to this more integrable systems perspective at the top. And so you combine, and then you want to try to prove the statements people have proved at the bottom in this full Stokes type picture. Okay. So for instance, if I go back to this picture, if you just take the compact story at the bottom, you're kind of missing the additive space, and you're missing the story about having different representations of the spaces as well. So basically there's a Théorie theorem that the moduli space is determined by the curve, and that's very far from being true in genus 0. So we get this serious problem of finding the isomorphisms between all of the spaces which occur. From the integrable systems perspective, it's the problem of finding a Lax representation of your differential equation that you want to solve. So I call that the Lax project, but it is just the representation theory of these like generalized Lie groups. So if you focus on the line in the middle and pass to moduli spaces, you end up with this picture here, which is really just repeating the red circle which I had before, these three different algebraic structures in the analytic space in the middle. Okay, so in the integrable systems literature, it's quite well known that this story started with this paper of Garnier. So it's over in this isomonodromy picture here, and he took the autonomous limit of it to pass over. So he did the higher dimensional version of this simplification that Painlevé did here. So he looked at the Schlesinger equations. These are the isomonodromy deformations of a Fuchsian system. So he basically starts with a connection on the trivial bundle having first order poles. He has something like the sum of AI over Z minus Ti, something like D plus this dz. And he looks at the equations for the isomonodromy deformations of that were discovered by Schlesinger just beforehand. Basically, this has to fit into a full flat connection, and the equation for the curvature of that being 0 is this equation here. So Garnier took the simplifié of this, he put in a parameter epsilon and let epsilon tend to 0, and he got this isospectral system here. And he calls this the simplifié because Painlevé used the word simplifié in this situation as well. And on the next page, he has his fundamental theorem. So first of all, he writes down the Lax equation here. So he multiplies his Fuchsian system by a polynomial such that rather than being a rational matrix, it becomes a polynomial matrix. That's this phi. And so you then get the Lax equation here. And this is basically the first example of a matricial isospectral deformation. And he then solves this in terms of abelian functions by defining the spectral curve. That's the algebraic curve f of x, y, which is here. The flows are constant on this. The coefficients of the spectral curve are independent of t. So this is the genus 0 Hitchin map, at least in the case where the bundles are trivial for GLN. And this was rediscovered in the Soliton papers. In particular, there's this paper of Adler and van Merbeke, and they look at the polynomial version, and they say it was also discovered in this work of Dubrovin, Novikov, and Manikov, I think. So he also, they also have this Lax equation there, and they solve it in terms of the straight line flows on the Jacobian of the spectral curve. So there is this story about people actually trying to solve differential equations explicitly here. So this is well known to experts on isomonodromy because one of the main papers on isomonodromy is this paper of Flaschker and Newell in 1980, and there's a section on this paper which makes the connection back to this paper of Garnier. It's not that I went back and discovered this paper. I read the main paper on isomonodromy in my thesis, and there's a section here which describes exactly what Garnier did. And there's also a paper of Chudnovsky which explains it as well. This is 1979. Okay, so that's a historical interlude there. Now let me go back to the sort of mathematical part. What is the definition of a good connection? What is the moduli problem that we think solves all of the problems, such that we do have all of these moduli spaces which match up? So basically, it's the algebraic description of what's going on in this paper with Bicard, and there's various papers which try to give clearer expositions of what's happening to sort of point out to more algebraically minded people what we think the right moduli spaces are. So for instance, here's a definition of the very good meromorphic connection. So it's a quite standard picture. There's a compact Riemann surface with a tuple of points, and we look at vector bundles on the compact curve, and we have a parabolic filtration in the fiber at each of the marked points. So this is a standard thing that goes back to Seshadri. And we look at a meromorphic connection, so having arbitrary order poles. And then we have to put in a compatibility condition between the parabolic structures and the connection. And we do this through a sort of a normal form, so such that at each pole there's a local trivialization which splits the parabolic filtration in each of the fibers, and such that the connection takes a particular form. So it has an irregular part, so this part has poles of order 2 or more, and this has to be diagonal, so it's equal to dq, where q is this diagonal matrix of polynomials in 1 over z. So that's the irregular type of the connection. So if I look at solutions of just the irregular part, I get things like e to the q. And so that's the reason we use the word wild, because they have these things like e to the 1 over z. And so the tame picture would be the case where the irregular type is equal to 0. And then there's a condition on the lambda, the formal residue. So first of all, it has to be in the Lie algebra that commutes with q. It's in CG of q, the centralizer of all of the coefficients of the irregular type, and also has to preserve the parabolic flags as well. So this is a quite familiar condition. If you take q to be equal to 0, this just means that lambda can be in the algebra of G, and it preserves the flag. So it's an extension of that in the presence of this irregular type as well. And that's the moduli problem that fits into this analytic perspective in this paper with Bickard. And then it's possible to do slightly more. You can look at the ones which are good, such that if locally at each pole there's some finite cyclic pullback which reduces to the very good picture. So there are these twisted cases also. But on any proper sector at the pole, it's isomorphic to the good picture, and so the analytical business works the same. So we fix Q, we fix the associated gradient of the residue and the parabolic weights, and that gives us a completely holomorphic moduli space of these meromorphic connections on parabolic vector bundles. And you can do completely the same in the Higgs picture. You just change the notation slightly, so you get the notion of a very good Higgs bundle as well. And so you can look at these moduli problems. So the thing that goes in the definition of the wild Riemann surface is this Q. But there's a slightly more geometric way of thinking of it, which was looked at by lots of people. In particular, there's a nice point of view of Deligne, but it really goes back to the definition of the formal solutions in work of Fabry, and it was extended by lots of other people as well. So geometrically, there's a very nice way to give the formal classification of algebraic connections on a punctured disk. So basically, I take the connection has a pole as a point A, I do the real-oriented blow-up of that to get this circle of directions, this D, this partial. This is the circle of directions at the pole, and the fact is that there's a covering space, this I, the exponential local system. It's a local system of sets, or a covering. It's an infinite union of circles. So there's this covering such that the connections on the formal punctured disk are equivalent to the I-graded local systems of finite dimensional complex vector spaces. So it is a completely topological description of the formal picture for the algebraic connections. This is important for us because all of the Stokes business is like how to glue this topological picture to the local system of solutions in the interior of the curve. So I just need to tell you what these circles are. So basically, you look at all of the functions, all of the exponential factors are functions of the form which are some polynomials in a root of z. So Fabry works out what all of the possible exponential factors are. And geometrically, you can look at the Riemann surface of Q. So basically, you define the Stokes circle to be the finite covering of the circle of directions on which this function becomes single valued. So the ramification of a Stokes circle is the smallest r, which is possible to put in this expression for Q. So each of these Q's determines this covering circle, the Stokes circle, and you can put all of these together to give this infinite cover, the exponential local system. And then the statement is that local systems on this covering space with compact support, so it has to be supported on just a finite number of the circles. So an I-graded local system at the bottom is the same as having a local system on the total space which has rank 0 except on a finite number of component circles. So if I have such a thing, there's just a finite number of these Stokes circles where you have rank greater than 0. There's this finite subcover, so there's a finite collection of Stokes circles, and on each of those you have a particular rank. So this defines the irregular class to be this finite formal sum of Stokes circles with an integer multiplicity. And that's the extra modular data that you want to include in the case of GLN. And in this formal picture, you also get the monodromy conjugacy classes as well to classify the isomorphism classes of the graded local systems are just the isomorphism classes of the local systems on the circle, and they're just classified by their monodromy. So this is a slightly more intrinsic picture than the picture with the Qs that we had here, and it's basically a question of if the eigenvalues of Q are ordered or not. Okay, so you can now draw pictures that solutions will contain these essentially singular functions like e to the q, and Stokes drew a picture in his paper of the growth and decay of this function x per q in the case of the Airy function. A simpler example might just be to look at the function x with x to the 17, and you would draw a picture here. So if you go on the positive real axis, it grows, and then after a bit it starts to decay, and then it has minimal decay, and then grows again. So that's the Stokes diagram of this Stokes circle x to the 17. So there's an intrinsic picture of having this circle as a cover, and then Stokes drew these non-canonical projections, which are useful in simple examples. But in the general case, you can't really draw these pictures. But nonetheless, there's lots of, most of the examples that you first meet, you will be able to draw these pictures. So Stokes looks at a version of the Airy equation which has Stokes circle 2x to the 3 over 2, and he drew this nice trefoil picture. So here the two branches have like maximal difference in their growth and decay on the real axis, and they switch over on these Stokes directions like this. And you can look at any other differential equation. If you look at, for instance, the Hermite-Weber equation, you get this. And there's a JavaScript program on my webpage that draws a particularly simple class. Basically, these are the ones which look like hypertrochoids. They're the equations which are the pullback of x to the 1 over b, where x is the inverse of z. And they're the ones which occur in a classical differential equation that was looked at by Mullins in like 1880 or something, and then it was studied a bit more by Turretin. And the ones that you pull back at the bottom are just the differential equations satisfied by the 0FQ hypergeometric series. These are the GLN version of the Frenkel-Gross connection, if I understand correctly. They generalized these hypergeometric equations to other groups. And so there's lots of other pictures. It's possible to draw all of the pictures of rank 2 differential equations. The 4 on the left here are rigid, so we know lots about the solutions of those equations. There's the Bessel-Clifford equation, the Airy equation, the Whittaker equation, the Hermite-Weber equation. And then the next two, you get to these ones which are minimally non-rigid. This means the moduli spaces, the symplectic moduli space, have complex dimension 2. So they have these isomonodromy deformations. This is the picture that you deform. This is the Stokes diagram of the equation you deform to get the Panelet-1 equation. So that will give you this if you look at the isomonodromy deformations of the corresponding linear differential equation. This is the one that you would deform to get Panelet-2, and then you get into the isomonodromy equations of higher dimensions. For instance, the two which are here. There's an example for rank 3. There's one for rank 4. There's some others as well. There's lots of different pictures it's possible to draw. The Bessel equation looks like this. It's basically a rotation of Whittaker. And there's the Bessel-Clifford equation, just as examples. Okay. So in the case of GLN, this leads directly to the definition that we want to make. So a rank n wild Riemann surface is a tuple with a surface with the marked points plus a rank n irregular class at each of the points. So we're stating that that's precisely what you want to deform. And if you deform it in an admissible way, there will be local systems of varieties over any such space of deformations. So that's the basic picture. You just need to choose these Stokes circles at each of the marked points plus their multiplicities. And then there's a definition of admissible deformation. So of course, this is in the spirit of Andre Weil's Bourbaki talk. I think the date on the abstract was wrong. It's actually 1958. So he talks about the surface de Teichmüller, which is an enriching of the structure of a notion of Riemann surface. It's a structure plus riche. And on the next page, he talks about these surface de Torelli. And if you read the paper of Delina Mumford, they talk about Jacobi structures as well. So there's the various different variations, and it's completely in the spirit of that. And of course, in the spirit of looking at a surface with marked points as well. Okay, but in particular, we have this generalization that accounts for the panel of A1 to 5 equations. So in this language, we can restate this non-abelian Hodge theorem. So basically, we need to choose the wild Riemann surface plus residue data. So basically, the conjugacy class around each of the Stokes circles plus the weights as well. And you do that in each of the pictures, in the Dirham picture and the Dolbeau picture. And there are moduli spaces which can be defined completely holomorphically, the Dirham moduli space and Dolbeau. And the point is, if you impose a stability condition, then that's the condition for the existence of a wild harmonic metric. So there's a hyperkähler manifold with a family of complex structures parametrized by the Riemann sphere. It's an analytic moduli space, but it involves Hermitian metrics as well. So it doesn't fit into the usual algebraic geometric picture, but it's a hyperkähler quotient, just as in Hitchin's original picture. But you need to do, there's a much stronger analytic package that was introduced by Bicard to handle what's happening at the poles in order to be able to solve these equations and get the moduli spaces analytically. And so you do that and you specialize. If you look in the complex structure 1, it specializes to the moduli space of meromorphic connections. And if you specialize to 0, you get these meromorphic Higgs bundles. And there's a statement about the metrics being complete if the residue data is semi-simple. So on each of the circles, your monodromy is, the associated gradient of the monodromy is semi-simple. And in the moduli problem, there are no strictly semi-stable points. Then the metric is complete. So in the paper, this is just proved in the untwisted case, but the same proof works in general. And we discussed it with Bicard like a decade ago, and it's the same thing. So the rotation of the weights. So the top part of this table, this is Simpson's table from his 1990 paper. There's basically a hyperkähler rotation from the Dolbeau to Dirham picture. That the main reason you need the parabolic weights there is that these get mixed up with the eigenvalues of the residues. So for instance, on the Dirham picture, the eigenvalue is this complex number lambda, and the real part of it is tau, and the imaginary part of it is sigma. But the tau here goes over and becomes the parabolic weight on the Dolbeau picture up to an integer shift. The sigma gets divided by 2 to be the imaginary part of the eigenvalue there, but the real part of the Dolbeau eigenvalue is this phi, which is the sum of theta and tau. So the weight gets added to the real part to become the Betty weight there. So if you do a meromorphic gauge transformation, so theta and tau will shift by integers in opposite directions, and that cancels out. So over on the Dirham picture, you see the affine Weil group, whereas on the Betty picture, you just see the finite Weil group. I got interested in that in like 2011 and wrote a paper about the G version of this, that this cancelling out of the affine part continues to work. So the irregular part gets imposed on top of it, and there's basically a factor of 2 in the change of the exponential factors. So it's possible to extend Simpson's table in this way. So in the tame picture, the hypercalar metrics, so Simpson has this bijective correspondence in his JAMS paper, but that's not enough to construct the moduli spaces. So Bickard had this paper on the analytic approach to meta and Seshadri, and his analytic package was used by Kono and Nakajima to get the full non-abelian Hodge diffeomorphism in this tame case. So Kono looks at the case where the Dolbeau eigenvalues are equal to 0, and this was upgraded in the rank 2 case in this short paper of Nakajima. But even in this case, the completeness was only proved in Kono's picture, where the harmonic metrics have finite energy. Okay, and there was a paper of Sabat that did the way to get harmonic metrics from irreducible irregular connections as well in 1999. And then, of course, in the compact case, this goes back to Hitchin and other people. And of course, if you take the Higgs fields equal to 0, in that case, you get back to this original theorem of Narasimhan and Seshadri. So I put a picture of Narasimhan here, who we lost recently. So I was a postdoc in Italy in 1999 to 2001. And so Narasimhan had just retired from being the head of the math department in ICTP. And this was back at the time when CISA was next door to ICTP. So I basically spent 2 years having lunch with Narasimhan. He had a lot of time to chat. And so that was a very sort of good period. I was a postdoc with Dubrovin, but Dubrovin was very busy and I did not speak to him as much as I would have liked to, but I did spend a long time speaking to Narasimhan, who told me about his trips to Paris, where he would come and go to the Chevrolet seminar, and Chevrolet would speak to him, and he never understood what en ce moment-là meant, because he was speaking very quickly and it was always a very puzzling thing. But perhaps the analytic aspects of this really go back to him, the way to get these extra Kähler metrics on the moduli spaces. So there's some mystery. I spent a long time thinking this was due to Atiyah and Bott, and then Goldman circulated a message that there's some proceedings paper of Narasimhan which did this first, and then if you look in the ICM talk, it's actually there on like page 2, that he has, I think the imaginary part of this is the Atiyah Bott symplectic structure. And it's this which I extended to the meromorphic case in my thesis, or the complexification of that. So yeah, there's sort of lots of history which is not so well known. Okay, so I wanted to talk about the Stokes data a bit. So I'm obviously kind of out of time, or a bit short of time. So I'll just talk about an example, and this basically goes back to Birkhoff. I'll specialize to GLN and just look at the local picture at a pole. So if you read the lecture notes or some of the papers, it will describe the general picture. Let me just sort of try to give the idea of how this works. So basically, there's a grading at the boundary. So here we just have a vector space which is graded by some set into these pieces, and we take G to be all of the automorphism of V and H to be the graded automorphism. So I have this like block diagonal subgroup. And we put H at one boundary and G at the other, and we draw this halo in the middle. And the Stokes business is really about how to glue a graded local system, so breaking it up, and the automorphisms all BH near the boundary, how to glue this to G. And so basically, there's a Stokes gluing which occurs. There's away from the singular directions it's possible to glue. This is just the topological expression of what the Borel summation or the multi-summation picture gives you. It gives you a way to associate an actual solution to a formal solution of a meromorphic connection. And we know that formal solutions are parameterized topologically by the graded local system here. And so what this summation gives you is a gluing to associate an actual solution. So think of the usual local system of solutions in the middle, an actual solution to a formal solution, which is a section of this graded local system here. And that is what happens. And we know the axioms of what this gluing has to obey. And basically, the monogamy around these tangential punctures has to be in the Stokes groups. And we know exactly what the Stokes groups are in terms of these Stokes arrows. There's a precise story which is there. And so at the end of the day, so for example, if you take a very simple case, which is something like, I don't know, A over Z to the K for a real diagonal A, then you get some picture like this, where all of the Stokes groups are these full triangular groups. The general picture, these break up into pieces, and all of the Stokes arrows are about how to parameterize all of the off-diagonal pieces which occur. So the basic picture is that there are these tangential punctures, and they each have a Stokes group attached to them. And you just look at all of the representations of the fundamental group, which has this grading, and the fact that the monodromy around these tangential punctures are in the Stokes groups. And this gives you a space of Stokes local systems, and you take the monodromy of those to get the Stokes representations. So an example of the wild representation varieties would be this. We frame at one point on each of the boundary. We have an H framing here and a G framing there. We look at the wild surface groupoid, so all of the paths in this curve with these extra punches, with base points on these 2 points here, and we can just write down explicitly generating paths to describe this space as just the product of G cross H and the Stokes groups. So G might be the monodromy or the connection matrix between these points, H is the monodromy around the H boundary, and these are the monodromy around the tangential punctures. So intrinsically, it's just the isomorphism classes of framed Stokes local systems. And then the statement you want to prove on these local pieces, you want to understand what is like the right analog of a symplectic structure there. And this is a quasi-Hamiltonian G cross H space. So basically in the tame picture, people had worked out what you need to put on such local pieces to be able to glue to get the global symplectic structures in a completely algebraic way. So the best way to understand what I mean by this is to look at examples in the tame case that people did before. So the theorem you want to prove is this, but you won't understand it unless you know what the words are. And so we pass back to the tame picture. This is actually the complexification. So there's very clean gluing point of view in this paper, Alexeyev, Malkin, and Meinrenken in 1998. There are lots of other perspectives as well, and this was just the particularly clean one that I was able to generalize to the wild picture. So you just look at the representation variety there, you frame at 1 point. The monodromy around the boundary can be expressed as this product of the multiplicative commutators like this. And they wrote down these axioms for quasi-Hamiltonian spaces such that if you just take the affine quotient directly, the quasi-Hamiltonian structure gives you an algebraic Poisson structure, and the symplectic leaves are got by fixing the conjugacy classes of monodromy. So they proved this by chopping it up into these pieces. You just need to know what's happening on these handles, these one-punctured elliptic curves, and then there's this fusion operation, how to glue together. So you actually only have to check the quasi-Hamiltonian axioms. It's a space with a two form which isn't closed, but like the derivative of the two form is the pullback of the canonical three form on the group along the group valued moment map. It's a slightly more complicated version of a Hamiltonian G-space. But having got that, you can construct all of these examples out of these basic pieces. So basically, there's the internally fused double and the fusion operation, and then the reduction is just this capping off. And so that's what they did. There's this toolbox and these operations. And so all of the spaces are just the fusion of these pieces, and then a conjugacy class at each of the punches or the holes, and then you reduce. So now we can just add to this toolbox. We have these fission spaces as well. So we get lots of new algebraic, symplectic, and Poisson varieties. We kind of accidentally constructed a lot more than we had planned to, because we just have these annuli with a G and an H boundary, and we can just glue them arbitrarily and have like loads of different H's and G's floating around. For instance, in this 2009 paper, I drew this. And so, for instance, I could have a GLB plus C, and it breaks into a GLB part plus a GLC part, the block diagonal subgroup here. So this proves that there is a natural algebraic complex symplectic structure on there. And the question I asked in this paper was, are these hypercaders? Is there some large generalization of the non-abelian Hodge picture, which works for these fission varieties, the class of varieties which are got by gluing and reducing all of these fission spaces. So I think that is still open. I don't think many people are even aware of this. But the main examples, the motivation was to understand these wild monogamy relations. I mean, I sort of read all the papers on isomonogamy in 1999, and one of the clearest papers was this paper of Jimbo Miranueno, who basically explained in a slightly better way what was happening in Birkhoff's paper. And they have an explicit wild monogamy relation. If you have a sphere with M marked points and all of the Stokes data there, you have a product relation like this, which is the generalization of the usual monogamy relation for a punctured sphere. But having seen that and knowing that there is this group-valued moment map business, you're just sort of dying to prove that the left-hand side here is a group-valued moment map, and so the reduction has a algebraic symplectic structure. So that's what was proved in 2002. And so these simplest cases of generic picture were where your H, your block diagonal group, is actually a torus. And so that's the first step there, where you have these toral boundaries. And then there's a story about how to extend it to arbitrary block diagonal groups. So that was actually proved for all reductive groups in 2002, but with this condition that the N was toral. It's the generic picture. And then in a sequence of papers, this got updated to the general picture. Even the case if you start with a local system of reductive groups in the interior of the curve, the ones which are not just twisted at the boundary, but they're also twisted in the interior as well. What we think is the most general picture. This is in this paper with Daisuke on the archive in 2015. And so at the end of the day, you get these twisted representation varieties with arbitrary structure at the boundary. And so you really just need to prove directly what's happening at the boundary. And even that is too complex to do directly. So there's actually an induction with respect to basically the order of the pole to glue the simpler fission spaces together. So basically, you might have an expression which is like this, z to the I, and you basically break it up into each piece and then glue these annuli in a nested way in order to get the structure. But once you have the structure at the boundary, you just plug it in and everything works smoothly. Okay. So the basic examples. So if I just look at this case of a pole of order 2, so Q has a pole of order 1. Your fission space is a product of G cross T cross U plus cross U minus in the generic picture. And if you just forget the framing on the G boundary, you get this. And the quasi-Hamiltonian business tells you that that has an actual Poisson structure. And it turns out that that's the Poisson variety that you're supposed to quantize to get the quantum group. And so people constructed the quantum group, and there's a choice for an integral structure there that you can put Q to be equal to 1 to get the algebra of functions on a non-linear version of the dual of the algebra. And Drinfeld calls this the dual Poisson-Lie group. And as a space, it's isomorphic to this product of the torus and the two full unipotent triangular groups. Now, it's not naturally isomorphic. There's a choice of the positive roots, which is basically coming from the choice of the A which occurs. And so this would be the case like this. And so the braid group action comes from the motion of the A. And so the simplest example of these wild mapping class group action that explains the quasi-classical version of the braid group action on the quantum group. So yeah, the gauge theory way to get the Poisson structure gives the same Poisson structure as what Drinfeld and people get from the quasi-classical version of the quantum group. This was proved a while ago, and so in particular, this is how these G braid groups occur in moduli of connections on curves, that the Drinfeld-Jimbo quantum group is the quantization of a wild Betty space. So it's modular in that sense. The next example, suppose you did this but didn't take A to be regular but just took it to be an arbitrary semi-simple, you would get a breaking to some block diagonal group H. And if you forget the framing at both boundary, you get this Poisson variety with symplectic leaves got by fixing the conjugacy class in H on the H boundary and in G on the G boundary as well. So you get some space. Now it turns out that these spaces are exactly the spaces which occur in the tame picture in genus 0. So here we're basically fixing the conjugacy class in H and in G, and you can actually describe this as a multiplicative quiver variety for a star. And that star is also the description of the tame character varieties. So there's a long story leading up to an appendix in Malgrange's book which explains how to transfer the Stokes data to the corresponding representation of the fundamental group. It's a very interesting story, and the ranks of the bundles changes. So basically the number of poles at finite distance on the tame side is the number of blocks in H here. But the fact is that the class of varieties which occur in this picture, just having one pole of order 2 and a pole of order 1, is the same as occurs in the tame picture, and you can prove that the symplectic structures match up algebraically as well. And Szilard-Szabo proved that the hypercalometrics match up as well, at least in the generic picture. So this leads to this idea of the representations of these group-like spaces, that you have a certain abstract space and it has these two different representations, either as a tame moduli space or as one of these very simple irregular cases. And this was also part of the motivation to look at the more general irregular picture, because the simplest irregular pictures for GLN are on the nose isomorphic to the tame picture, but then there's lots of others which aren't as well. Okay, so let me just get to the graphs. There's a whole story about how in these simple Panlevey examples that these are related to affine Dinkin graphs. And so there's this theory of Nakajima quiver varieties, which if you look at the cases of type E, these come from the symmetry groups of the tetrahedron, oxyhedron, icosahedron, and there's a way to construct these singularities and their resolutions directly in terms of the graph. This goes back to Kronheimer and then generalized by Nakajima. So you can draw the graph, and there's a way to look at arrows on the graph which does this, which is reasonably well known. And the fact that these are dimension 2 and they're related to affine graphs is coming down to this formula that the dimension vector is a null root. But these are modular. They are moduli spaces of Fuchsian systems. So you can do the symplectic reduction in a particular way to get to a very concrete space of Fuchsian systems here. So that explains the E-type graphs as moduli spaces of connections with 3 poles. These are the ones with three legs. And then you remember that there's a 4th star-shaped affine Dinkin graph, perhaps actually the most interesting affine D4. This has 4 legs, and so the corresponding Fuchsian systems have 4 poles. And so this is what actually leads to the Panlevey 6 equation, the tame Panlevey equation. You look at the corresponding local system of Betti spaces over the space of cross ratios of these 4 tuples of points, which correspond to the 4 legs which are here. You can then pull it back to the corresponding de Rham side and then restrict to this open part in which we have explicit coordinates. And that is what the Panlevey 6 equation is. It's an explicit expression for this non-abelian Gauss-Manin connection. That's really just a different way to rephrase the way it was discovered by Richard Fuchs. And over here we have the Betti spaces, which have a familiar expression as well. So Okamoto did some very nice work on Panlevey 6, and he found that there's a natural action on the base of the affine Weyl group, whereas in the Kronheimer-Nakajima picture, you have the finite Weyl group acting. In this Panlevey picture, sort of a reflection of the fact that we're over on the group side, you naturally have the action of the affine Weyl group here. And so, yeah, there's this paper of Okamoto relating between the Panel-Wehr equations and the Dynkin graphs. The six cases of the affine Weyl groups which occur are these. The D4 there, and there's various ways to conflue to get the irregular cases, and he computed the affine Weyl group there. So the question becomes to understand why we're relating, say, A3 to this panel of A5 case, which is to do with one pole of order 2 and two poles of order 1. In the panel of A6 picture, it's reasonably clear how the four poles are related to the four legs. And so there's a long story about how to read the affine Dynkin graph from the moduli problem there, and then how to extend it to arbitrary dimensions. So this is a question I've spoken about a lot before, and it sort of works reasonably well in the cases where M star is a Nakajima-River space, and there are these twisted ones where the open part isn't, and it's trickier. And then my plan was to talk a bit about that, but let me just skip over it. There's various questions, and you get to this picture here of a theory of like Dynkin graphs to try to parameterize these spaces. So at the moment we're trying to characterize exactly what is the class of graphs that characterize the genus 0 non-abelian Hodge spaces. Okay, so maybe I'll stop there because I think I'm out of time.